In this video, we're going to do a review of logarithms just to get back into the swing of things with what it means to evaluate a logarithm, review that skill of estimating a logarithm, look at natural logarithms or log base e, and then look at the change of base formula. So how do you convert from one log base to another? So just to kind of get back into the swing of things with what a logarithm is, remember that the output on a logarithm's an exponent. The output on a logarithm's an exponent. So again, this is asking you 2 to what power gives me 8, and so that power is 3. So if you want to take a moment, if you want to practice that skill of evaluating logarithms, you could certainly pause the video here and then do these other 5 on your own and check the answers. If you want to review, you can go through it with us, but I know some of you wanted to work on that skill. All right, so a log of 0.001, so some people like to write that as tens, hundredths, thousandths, 1/1000th is a way to write that decimal as a fraction. There's no log base written, it's the common log, so 10 to what power gives me 1/1000. So I need to take the reciprocal and then I need to cube it. 7 to what power gives me 1/49. I need to take the reciprocal of 7 and then square it. 4 to what power gives me 32. Well, 4 doesn't go straight to 32, so this one's going to have a rational exponent. So I need to root the 4 first. I can only square root the 4, so when I square root, that's a 1/2 power. Then I think to myself, 2 to what power gives me 32? Well, again, that's 2 to the 5th power. So remember, the power goes in the numerator and the root goes in the denominator. Okay, same thing is going to be here with log base 9 of 27. 9 to what power gives me 27? That I have to root the 9 first, and I can square root 9. When I square root 9, then I think 3 to what power is going to give me 27. That's 3 cubed, so 3/2 power. 25 to what power gives me 1/5? Well, a reciprocal had to occur to get from 25 to 1/5, so the answer is negative. And then I need to square root the 25, and a square root is a 1/2 power. All right, so another skill that we've picked up in previous lesson is estimating logarithms. So that skill comes in handy in just having a good number sense with logarithms. It can also help you check the reasonableness of answers in an application context. So let's go ahead and estimate log of 3. So again, there's no log base written, so it's saying, hey, 10 to what power gives me 3? And so in previous lessons, we talked about finding the 2 integer exponents that this falls between. We can continue with that, but also try a little bit more to estimate, pinpoint it to a little bit closer to one value. And so 10 to the 0 power is 1, and 10 to the 1 power is 10, and so 3 falls between those. So the exponent's going to fall between 0 and 1. But since 3 is closer to 1 than it is to 10, the exponent's going to be closer to 0 than to 1. So if you had wanted to estimate, like, I'm just kind of estimating like 0.2, so a number closer, an exponent closer to 0 than 1. So again, that's my estimate. And so we'll check that, verify it with the calculator. So we can do log of, get it turned on here. So log of 3 is I was off on my estimate, 0.48. Okay, so if you want to practice that skill of estimating, you could pause the video now and try to estimate these. So again, the estimating would come before the plugging it into your calculator part, otherwise you're not really estimating. Okay, so 10 squared is 100, 10 cubed is 1,000, 120 is closer to 100, so maybe like 2.1, because it's between 2 and 3. Go ahead and check it out. All right, so that's pretty close, 2.0 8 that time. So again, a little bit closer. Okay, so log of 0.05. So 10 to the negative 1 power is 1/10 or 0.1. 10 to the negative 2 power would be 1/100th, which is 0.01. So 0.05 falls between those, and 0.05 is closer to 1/100th. So some number between -1 and -2, but closer to -2. So like maybe -1 point. Well, and it's not really close to 0.01, so I don't know, like maybe -1.6 or something. Let's check it out. So log of 5/100ths. All right, so -1.3. All right, so again, that's the skill of evaluating logarithms, estimating logarithms when we're not able to find the exact answer using mental math, and then using technology to verify the result. So the next topic that we're going to look at, that we looked at briefly in other lessons, was the log base e. So the PERT model is used in many different fields for the compounding continuously model, and so we need to have an inverse of that base, exponential base e, so that's where the natural logarithm comes in. And so it's always written like this, but just to give you context, it's written there as log base e to help it make it easier for you to understand. So again, whenever we see this natural log notation, it is a base e. So since this is a logarithm graph, the graph shape looks similar to our other parent logarithm functions. So if we had the equation like y equals natural log of x, that is like y equals, that's that log base e. And so if I rewrite that in exponential form, e to the y power equals x. So some ordered pairs that are on there, like if we tried 0 and 1, like e to the 0 is 1, anything with the 0 power other than 0 is 1, e to the 1 is e. And so if I go ahead and take a look at the sketch, I see the point 1, 0. I see the point E1. Remember that E is, approximately 2.71. Okay, so the domain of this function is still x is greater than 0, just like all the other logarithmic functions. And my range is all real because my exponent can be anything. And so the part that's trickier is since e is not an integer value, it's a little bit harder to get some of those other integer ordered pairs. But again, the natural logarithm graph looks just like the others. And so in case you haven't seen it before, that it's right below the log button. So there's natural log. So just in case you're looking for it. If you had wanted to graph natural log and you had wanted to check that out, that's where you find it. Your calculator doesn't do a very good job of sketching vertical asymptotes, so don't expect to be able to read that clearly. All right. So since this doesn't have as many integer ordered pairs, that our graph will be a little bit more of a sketch maybe than some of the other logarithm graphs, that this is the parent graph translated to the right 3. Excuse me, right 2. I don't know what I was thinking. My apologies. And so my asymptote that was at x equals 0 shifts to the right 2. And my x-intercept that would have been here at 1, that's going to shift to the right 2. And so I'm not worried about plotting as many points accurate, but notice that my sketch has a correct vertical asymptote, and it has a correct x-intercept. So for this circumstance, that if you know that about this graph, you actually have and you have the right shape, you have a pretty good idea of what this function looks like. So again, the domain is x is greater than 2, since that's translated 2 to the right, and my range is all real numbers. All right. So just kind of practicing that skill of estimating logarithms, let's go ahead and estimate a couple natural logs. So if I want to find natural log of 10 and estimate that, remember that natural log is about 2.7. So you can think of maybe e to what power gives me 10. Or if when you're in your mind, you're thinking 2.7 or even 3 to what power gives me 10, like that can even thinking about 3 can give you a good feel for it. So 3 squared would be 9, but e is less than 3, so you know, somewhere around 2, right? So I think it can sometimes be difficult to estimate since e is 2.7. That's a tricky number to work with. So if I just test it out just to see, thought I hit the quit button. If I go natural log of 10, that I get 2.3. So although just saying 2 isn't a really close estimate, again, it gives you just some number sense and some context. All right, natural log of 64. So again, e to what power gives me 64. And again, for estimating purposes, you might want to roughly estimate e is 3. So 3 to what power gives me 64? Well, 3 cubed is 27. 3 to the 4th, that's 81. So maybe somewhere between, around 3 or 4, like somewhere around there, like 3 to 4-ish. Again, it's just nice to have some number sense with that. And so again, since 2.7 is less than 3, that's why that number is a little bit bigger, so 4.16. Okay, so again, estimating with the logarithms, that's a little bit easier to get a more accurate estimate, but I just want you to have a feel for what the numbers would be. All right, so sometimes you need to be able to switch from one log base to another. And so that there may be a reason for that. Maybe you need to switch log bases to simplify and apply a log property, or maybe you need to switch log bases when you're solving an equation. So there are some different reasons for that. And so that there's a formula here. It has a lot of letters in it that allows you to switch from any log base to any new log base. Okay. So if we zoom in on this and take a look at it here quick. So let's say I had something that was log base b of m, and let's say I wanted to switch it to be log base c. The conversion is log base c of m divided by log base c of b. So log of my new base of my input divided by log of my new base of my old base. We'll practice on a few more, but I just want to keep it while it's zoomed in here, look at it. So let's say I had like log base 6 of 7. I just made something up. Let's say I want my new base to be base 8. Again, I'm just making something up. So according to this formula, it's going to be log of my new base of my old input. So see how that's there? And divided by log of my new base of my old base. So log base 6 of 7 is equivalent to log base 8 of 7 divided by log base 8 of 6. So again, you can use it to go from any base to a different base. We most commonly find ourselves going to to convert ours from any log base to a common log or a natural log. That's usually the conversion that you see occur. Okay, so if I want, we'll do some of each. So the ones in this column will convert to a common log, and the ones in this column will convert to a natural log. So log base 81 of 27, if we want to convert that to a common logarithm, that would equal common log of my old output divided by common log of my old base. Okay. And so that would allow me to go from log base 81 to common log. So it's a conversion formula. So I know it doesn't look like it, but when I say conversion, it would be similar to saying 12 inches is 1 foot. We're just rewriting it using a different unit. In this case, we're rewriting it using a different log base. So log base 8 of 32, if I wanted to rewrite that as a common log, I could be common log of 32 divided by common log of 8. Okay. And so, like if you had wanted to get a value for that on your calculator, you have a common log button pretty handy. So log of 32 divided by log of 8. Okay, and so that turns out to be 5/3. I didn't ask you to evaluate it. I just wanted to show how the skill of converting to a common log, how technology can play a role with that. And so if we think about this, again, it's saying 8 to what power gives me 32. Well, if I cube rooted the 8, I'd get 2, and 2 to the 5th is 32. So hopefully that makes sense. I would say it's equally as common to go from a log base to a common logarithm as it is to a natural logarithm, that they're equally as common. No pun intended there with the common log. So if I had log base 5 of 36 and I wanted to rewrite that with a natural log, I would rewrite that as natural log of 36 divided by natural log of 5. And so again, you can go from any base to any new base. If you don't like natural logarithms and you like common logs better, you also could have written it as log of 36 divided by log of 5. It'll all end up having the same value. So if we were to look that up here on or work that on our calculator, I just wanted to verify with you that we get the same answer. So natural log of 36 divided by natural log of 5. So 5 to what power gives me 36? That's about a 2.2 power. Similarly, I'd get the same result if I did common log instead. Okay, so it does yield the same result. And so just so that you're aware that that's how that formula works. All right, so log base 4 of 18. So if I try to think about and estimate that in my head first, I think 4 to what power gives me 18? Well, 4 squared is 16, so I bet it's going to be pretty close to 2. So if I did natural log, it would be ln of 18 divided by ln of 4. If I did common logs, it'd be log of 18 divided by log of 4. And yep, if I did that on my calculator, so log of 18 divided by log of 4, I end up getting 2.08, or yep. Okay. So again, you can go from any log base to another base. So if you had wanted to try the formula out, maybe you should pause the video now and try these couple and then check together with the video in just a second. Okay, so I got 3.17 and 2.56. Again, just as a reminder, this can allow you to go from any log base to any other. So you wouldn't want to do it because you don't have this button easily accessible on your calculator. But again, you could have, if you were looking at log base 2 of 9, you easily could have even switched to like log base 47 if you had some purpose for that. That it would be log base 47 of 9 divided by log base 47 of 2. So again, I know that seems kind of weird, but I just want to drive home the point that you can go from any log base to any log base of your choosing. So again, in this lesson, we reviewed evaluating logarithms, estimating logarithms, introduced a little more in depth the natural logarithms, and then the change of base formula.